Hey everybody, Dr. A here, and in this video we're going to be exploring another example of using deflection formulas. So let's go ahead and get started. In the given information, we're being asked to compute the magnitude of the force P, and we see that here at the free end, that should be applied at the free end to give a delta value of 0 at that free end, and we're also being told that EI is constant. So here we have this cantilever beam. This is a fixed connection on the left side. It's 3 meters long, and it has a triangular load applied, and in this case this is a linear decreasing load. It's starting out at a high point of 0.5 kilonewtons per meter at the fixed connection, and it linearly varies down to 0 at the free end. And then we're proposing to put a applied load P at this free end, and that's what we're trying to find. We want to find what this P load is so that delta will be 0 at that free end. So how are we going to approach this? Well, we can go ahead and say by superposition we should have the following. Well, we'll have the triangular load here. Okay. And of course there's the 0.5 kilonewtons per meter. And we see a 3 meter length. And so when this load is applied, what do we have? Well, we're going to have this curved deflected shape, and this is going to be delta 1, okay? And we can say the effect of that can be added to the effect of applying a load P at this free end. 3 meters long still. And what is that deflected shape going to be? Well, you have a taper just like before, except it's curving up now. All right? And so this is going to be, call it maybe delta 2. All right? And so how are these related? Well, you were told in the problem statement that we want delta total to be 0. So what we're going to do is we're going to say by superposition, we're going to have delta total is equal to negative delta 1 plus delta 2. But again, delta total is going to be 0, right? This is going to be 0. So what we're really saying is 0 equals negative delta 1 plus delta 2, okay? And so what is this delta 1? Well, we're going to get this pre-derived formula for this particular load case, linearly decreasing load on a cantilever beam, okay? And so we can substitute that in just like we've seen in some of our other examples. That's going to be negative W L to the 4th over 30 EI, and then we're going to add that to delta 2, which is going to be PL cubed over 3 EI. And you can get these from any deflection tables from any mechanics of materials book. Now here's the thing to be careful, okay? This negative here is the same as these negatives that I showed in the previous couple of steps, okay? This is indicating a downward deflection, all right? And then the positive sign in front of delta 2 is indicating an upward deflection due to the presence of P. And sure enough, this red P is the same as this P, okay? And that's what we're looking for. So let's start substituting values in. We're going to say 0 equals, and we're going to say 0.5 kilonewtons per meter times 3 meters to the 4th power divided by 30 EI plus, here's our red P, times 3 meters cubed over 3 EI. Now, you might have noticed earlier, one step before, we could have gone ahead and canceled some stuff, right? I mean, we could, because again, this equals 0, right? So you can say the EI cancels. You can say this L cubed cancels with 3 of these L's. You can say this 3 cancels with this 30 and becomes a 10. So we could have done a lot of rearranging already just from the algebra perspective before we substituted values in. It doesn't really matter, but again, you know, just keep that in mind. Your algebra can be shifted around. In either case, what we finally end up with is P equals, and let's see what comes of it. You should just move you know, that negative term to the other side of the equation, so you'll get 0.5 times 3 over 10. And so you should end up getting a value of 0.15 kilonewtons, pointing upward, of course, okay? And again, what this means is this would be the force P that you would have to apply at this free end to cause this beam to not deflect at that point, at that specific point, okay? So that concludes this example. If you found this helpful, please hit like and subscribe and be on the lookout for other content like this. Thanks for watching.